All right, we're going to continue with our discussion about reliability and validity. This is a fairly short video. I'm going to introduce you to the concept of reliability and validity. Then I'm going to talk to you about various scales of measurement, and then we'll be done. So, what is reliability? The word reliable means dependable, stable, or consistent. So when we talk about the reliability of a measure, we are talking about the relative consistency of a measure. In other words, if I were to give the same measure over time, would it give me the same or very similar outcomes? And the more consistent the outcomes, the more I can say the measure is reliable. So, however, we know that even reliable measures have some level of error. So, anytime we measure or we collect data, the score that you get, which we refer to as the observed score, is equal to your true ability plus error, or your true score plus error. So, let's say you were taking an exam and you got a 92 on a psychology exam. Does that mean that that was your real ability? No. It's possible that some of the questions were flawed. And because of the flaws that were built into the questions, you got a question incorrect. So we know that all of us as professors, we know that any test we give has some degree of error, and we want to minimize the amount of error as possible. So reliable measures have a great deal of ability to predict your true score, and they have very minimal amount of error. So reliable measures have the goal is to have as little error as possible. All right. So it's important to understand, though, that if you don't have a reliable measure, then you have nothing. So let's say you were to get on your bathroom scale, and you get on your scale, and at one time you get on a scale, it says 150 pounds. Another time you get on the scale, it says 120 pounds. And another time you get on the scale, it says 135 pounds. And these measures were within minutes apart. It's reasonable to suggest, well, there's something wrong with the scale. It's not producing a consistent output. Therefore, the conclusions about weight that are made from the scale cannot be done. So remember the principle of GIGO, garbage in equals garbage out. So if you don't have a reliable measure, then we can't even move forward. There's oftentimes a question, can something be reliable but not valid? Can something be valid but not reliable? The answer is yes, it's possible to be reliable but not valid. However, if validity refers to accuracy or precision, if something is inconsistent and it's all over the place, then it's not accurate. So reliability is a precursor to validity, not the other way around. Now, trying to replicate a study using an unreliable measure is just going to frustrate you. You're going to discover that because it's unreliable, you can't get the same output or similar output. So the ability to reproduce or replicate a finding is going to be hindered because of unreliable measures. Now, if you want to increase reliability, it's very important to train the observers if you're doing observational research. If you're doing survey research or interviewing, make sure that the way you phrase the questions are done carefully and with a decent amount of thought about how they're phrased, because if you're not consistent in how you phrase things, you might get inconsistent responses by the wording of the question. And even in neuroscience, you have to make sure that where you place the electrodes, you're doing it in the same spot across participants or subjects. Now, here's an example of what I mean by reliability. Let's say that you gave a person an IQ test, and you gave the person an IQ test 52 weeks out of the year, and one administrator, their average IQ for this person was 100, which is average, but the range of scores between the 52 weeks was 97 to 103. Now, the problem with this example is that you might be creating a practice effect. So disregard the fact that you wouldn't actually give an IQ test once a week. But let's say you did, and you were used different measures of IQ, and one administrator, their scores ranged between 97 and 103 with an average of 100. And another administrator, they got the same average of 100, but their scores range from 85 to 115. Which one are you gonna say is more reliable? Obviously, the one where the scores are tighter together, more consistent. So the tall, skinny bell curve would be considered the more reliable measure because it has less error at the tails, whereas the flatter bell curve would have more error. Okay, so that's one example. Now, how do we assess reliability? Well, there are many different ways to assess reliability. And one of the ways we assess reliability is through a correlation. And we talked about correlation in previous lectures, but a Pearson product moment correlation measures the relative association between two or more factors. And as long as both factors are interval or ratio data, you can run a correlation. Now, the more reliable the measure, the stronger the association is going to be, right? So the closer it is to the absolute value of 1, whether it be +1 or -1, the stronger you're going to say the consistency, and the more accurate your predictions are going to be. So now, as I've mentioned in previous lectures, the correlation has two components. The sign, whether it's positive or negative, tells you direction. And then the number tells you strength. So positive means both factors go in the same direction. So they either increase or decrease together. Whereas a negative correlation, they go in opposite directions. So as one increases, the other one decreases. But very reliable measures are going to have correlations closer to 1. All right, so here's just another graphic of correlations, negative or positive, and the spread of possible correlations you could get. So in addition to a correlation, we could do test-retest reliability. Now listen to how I define it because it's crucial. Test-retest reliability is when you give the same test to the same people at 2 or more points in time. Now, I emphasize the fact that it's the same test because when you give the same test, you can create potential problems with your reliability score. Now, with test-retest reliability, you're going to correlate score at 0.1 and the correlate score at 0.2 and see link how associated with they are. For test-retest reliability, as long as it's 0.8 or stronger, we say we have some sense of reliability. Now, I emphasize that the same people are getting the same test because that creates a problem. And the first problem with test-retest reliability is what we call artificiality. And artificiality means that it's possible that we get a strong relationship between testing at point A and testing at point B, but it's because they remembered the answer and they answered similarly. So we create a strong relationship between the two, even though it may not be an accurate representation. So one solution presented is to have alternate forms reliability. And when we talk about alternate forms reliability, we're giving, listen to the change, different versions of the same test to the same people at 2 or more points in time. Now, what you've done is you've eliminated the problem of artificiality because you can't remember the answers because they're different questions. Now they measure the same construct, so there's going to be an association between them, but you can't just artificially answer. Now, whether you use test-retest reliability or alternate forms reliability, you can't get out of the problem of maturation. And maturation is another factor that could influence your reliability score. So it's possible that there was some kind of transformation between point A and point B, and that created a difference in the responses. So whether you're using the same test or a different version of the test, if there was some growth that happened from point A to point B, that's going to create a problem for the reliability. So whether you use test-retest or alternate forms, you're going to have an issue with maturation. Now, the previous two examples that I gave, whether it's test-retest reliability or alternate forms reliability, require you to give a test at 2 points in time. Let's say that you didn't want to have to track people through time and have to contact them a second time to do another test. Or let's say you just wanted to be over with your assessment of reliability with administering a test at 1 point in time. You can do that. And there's a way to do it. So when we talk about test instruments, we can assess something called internal consistency reliability. Now, what is internal consistency? Instead of testing between 2 points in time, we're comparing part of a given test with another part of the same test. And we divide that test at a minimum in half. And that way of doing it is called split half reliability. So we take, I don't know, let's say it's a 60 item test. We take odds versus evens. So 1, 3, 5, 7, ... all the way to 59, 2, 4, 6, ... all the way to 60. And we have people answer the test and we correlate the scores on part A and part B. And we would expect a strong relationship. Now we don't have to test you at 2 points in time. We could test you at 1 point in time. Now, split half reliability is good. And it's always good to do odds versus evens rather than first half, rather than second half, because people get bored. So you could create artificiality. So odds versus evens addresses that problem. So, but one challenge you get is you get one correlation. Now, there's a better way to measure a test, and that's called Cronbach's alpha. And in a Cronbach's alpha, you correlate each individual item with every other item on the test. And when you do that, you could set it to tell you how strongly related each item is with one another. You can get the alpha of the Cronbach's alpha if you were to omit a particular item, and it tells you the relative strength for each item relative to one another. With Cronbach's alpha, you want an alpha, which is the average of all correlations, to be 0.7 or higher. So if you had a 10-item test, you're going to get a lot more correlations because you're going to get a correlation with item 1 to 2, 1 to 3, 1 to 4, 1 to 5, all the way to 1 to 10. And then when you go to item 2, you're going to go 2 to 3, 2 to 4, 2 to 5, and so forth. And then you get all these correlations, inter-item correlations, and then you do an average of all, and that's your alpha. Now, when we're developing instruments, this is part of the process in reporting for reliability. So when you develop an instrument, you have to report Cronbach's alpha. You have to do a factor analysis, which clusters items together. And you do two factor analyses, an exploratory factor analysis, which is your first time running this study. And then you do a confirmatory factor analysis, which is with a second sample, and you see if you get similar factor loading. And then if there are items that need to be removed or excluded between sample 1 and sample 2, you do that, and then you have a final instrument. But so notice how we're taking one instrument and looking at the consistency of that instrument within itself. And that's why it's called internal consistency reliability. And the two subtypes are split half for Cronbach's alpha. We also have something called inter-rater reliability. So this is if you're doing observations and you have multiple raters scoring a behavior. You can do inter-rater reliability. We anticipate that the raters will be relatively consistent with one another. And there's a statistic to test inter-rater reliability called Cohen's kappa. Now you're like, well, when would you have inter-rater or inter-judge reliability? The best example I can give you is in the Olympics. In the Olympics, let's say you have gymnastics or figure skating, or diving. The judges have a strict rubric, and oftentimes they're very close in scores to one another, whether it's 1/10 of a point off or 2/10 of a point off from one another. Very rarely do you get 3/10 of a point off. If you ran a Cohen's kappa for Olympic sports, you would see strong, tight correlations between the raters, a strong inter-rater reliability. There are other sports that don't have the same inter-rater reliability, that have multiple judges, like boxing. Oftentimes, you have what's called a split decision, where one judge said person A won the boxing match, and another judge says person B won the boxing match. How does that happen? Well, the way they scored it was very different. And that's an example where you might not have as strong of a Cohen's kappa. Now, I talked to you about reliability, which refers to consistency of scores. But just because something is reliable does not mean that it's valid. So you can have something that is consistent, but consistently inaccurate. What's a good example? Simple. A broken clock. A broken clock will say the same time every single day. And all but 2 minutes in a day, the clock is going to be wrong. It's consistent in its reporting of time, but it's not accurate, if that makes any sense. So let's talk about validity. When we talk about validity, validity refers to accuracy or truthfulness of the representation. And there are 3 types of validity, and I'm going to go out of order from the slides because I think it's important. Internal validity is whether we can draw conclusions about causal relationships from our data. So another way of saying internal validity is to what degree can we say our independent variable caused changes to our dependent variable, or whether there was some other confound that played a role. And in chapter 8 or lecture 8, I'm going to talk a little bit more about the concept of the relationship between internal validity, the independent variable, the dependent variable, and the issue of confounding variables. So, moral of the story is if you eliminate confounds, you have greater internal validity. If you allow confounds to creep into your study, then you weaken your internal validity. So that's internal validity. External validity is the generalizability of your study. How well can you generalize from your sample to the population at large, from your study to the real world? And depending on how you design it, you may have greater or lesser external validity. Now, we talked in a previous lecture about your decision to either use a laboratory experiment versus a field experiment. And one of the benefits of a lab experiment is that you have a very controlled environment. And because you have a controlled environment, laboratory experiments have strong internal validity. However, one of the criticisms of laboratory experiments is that they might be artificial and they may not generalize to the real world. So lab experiments have potentially weaker external validity. Whereas field experiments, one of the benefits is that it replicates the real world. So external validity is going to be increased because it mirrors the population at large. However, I said because it happens in the real world, field experiments, you lose some level of control over confounds. And because of that, we say field experiments have weaker internal validity. All right, so that's internal and external validity. Last but not least, I want to talk to you about construct validity. And in psychology, we use a lot of terms that are very abstract, such as anxiety, love, intelligence, personality. And if I were to ask you to define these terms, you might define them one way, and another researcher might define them in a very different way. And I know I mentioned in a previous lecture the importance of operational definitions to have a common language. But let's say I was creating a new test called the Kaplan Intelligence Test, which I give a mnemonic called the KIT. And I wanted to test my KIT against other measures. Construct validity would, in general, look at how well does my Kaplan Intelligence Test truly measure intelligence? So how well does the instrument or operational definition actually measure the construct it's claiming? Does that make sense? So we're testing the instrument or operational definition against the theoretical concept as a whole. And the more accurately it depicts that theoretical idea, the better it is. So, but we need to have ways of testing construct validity, right? So we talked about the definition, but there have to be ways to test it. And the first test of construct validity is something called face validity. And when we look at face validity, we're looking at face value. If you look at it and I were to ask you, look at this test, what do you think it's measuring? If you can say, well, I think it's measuring intelligence, then it has face validity. It appears to be measuring the construct that I allege it's measuring. Now, face validity is great, and it is one metric of construct validity, but it's not enough to say that we have a valid instrument. Why is that? Because looks can be deceiving. So there are going to be instruments that are more subtle in their assessment that may not look like really good tests of a construct, but they're good. And then other things may look really good, but not be very good measures. So in addition to face validity, we have to have other measures. So we have criterion-oriented validity. And criterion-oriented validity looks at how the relationship between the scores on a measure and a given outcome. And one of those particular criterion-oriented validity is predictive validity. When I give you this test, does it predict something else? So if I'm using the example of an IQ test, does it predict your performance in a classroom, right? That would be useful. Other predictors might be your SAT or your LSAT for law school, or your MCAT for medical school, GRE for graduate school in general. So these instruments predict success at the next level of college. So that would be predictive validity. Concurrent validity examines whether groups of people differ on a measure in expected ways. Can the instrument separate out different levels of performance based on a given factor? So if I have an IQ test, it should separate out high IQ, average IQ, low IQ. Should get a nice spread of scores. And that instrument at the same time, concurrently, should be able to separate out different levels of performance on the test. Now, another strategy to test construct validity is convergent validity. And in this particular case, you're taking two measures of a particular construct and correlating them. So if I were doing an intelligence test that I were creating, my Kaplan intelligence test, I would have to give a person the Kaplan intelligence test as well as the Wechsler intelligence test. And their performance on the kit should predict their performance on the Wechsler test. In other words, two measures of the same theoretical construct should get you the same outcome or very similar outcomes if it's valid. So the scores should converge. They should come to the same point or a very similar point. Discriminant or divergent validity is the opposite. It's the inverse of what I said. Two measures of two different constructs should get very different outcomes. So the Kaplan intelligence test compared to a happiness scale. Intelligence has nothing to do with happiness. So they should not cluster together. They should not be correlated. They should get very different scores because they're different measures of a different theoretical construct. And here is just a summary slide that talks about the various types of construct validity, face validity, criterion-oriented validity, and the subtypes. And here is another example of the three subtypes of validity. Internal validity, as I said, is the extent to which you could say your independent variable caused changes to the dependent variable. And the question I want you to think about is, are there alternative explanations for this outcome that this study did not address? If you can think of them, you potentially have a confound or a threat to internal validity. External validity, as I said, was your ability to generalize from your sample to other to the population at large or to the real world. So questions that are related to external validity include, can the results be replicated with other participants? Or can the results be replicated in another setting? So these, to the extent that they can be replicated, the more consistency you have across situation, the greater confidence we have in the generalizability of the outcome, or external validity is increased. Construct validity is evaluating the adequacy of an operational definition. So questions you might ask in this vein is, does the operational definition sufficiently measure the construct it claims to measure? And I just gave you a whole bunch of ways to test that. Now, let's say you're not sure what instrument to use. Well, there are different ways to approach this. And I'm going to make a different video on how to search for instruments using psych tests through the library. But one of the most robust tools is something called the Mental Measurements Yearbook. And that gives you a list of all the tests of a given construct that have been developed to date, their strengths, weaknesses, their scoring procedures, and so forth. It comes out every 2 years. Bureaus publishes it. It's really, really good. Now, we also have something called psych test, which comes from the American Psychological Association, and then they give you an actual copy of the test and the scoring procedures. Now, when you do any kind of research, you have to be mindful of concepts like reactivity. Reactivity, in principle, is that when people are being observed and they know that they're being observed or being watched, it changes their behavior. And whether you're doing a survey, whether you're doing an observational research paradigm, or whether you're doing an experiment, when people are part of the study, their behavior might change from how they behave in the real world, which is also a threat to the accuracy of your conclusions. Now, there are ways to deal with reactivity. One way is to give time for people to get used to being watched. And as you give people time and they get used to you, they start to behave more naturally, more normally. A second way, especially in public places, is called non-reactive measures or unobtrusive measures, where you observe the variable without them knowing you're watching. So because of that, they behave more naturally because they don't know that they're being watched. An example might be using a one-way mirror. You can see what they're doing, but they can't see that you can see. They can't see you on the other side. Now, the next thing I want to talk to you about are scales of measurement. So there are 4 scales of measurement: nominal, nominal, ordinal, interval, and ratio. And you have a mnemonic to remember the 4 scales of measurement, noir. So if you speak French, noir is a word that means dark or black. So N of noir stands for nominal. So when we're looking at nominal measures, we're dealing with variables that are categorical in nature. They do not possess numerical qualities. And we can report frequencies, how often they occur, but the frequencies does not necessarily mean greater or better than. They just mean more frequently occurring or less frequently occurring. Examples of categories might be gender. And in psychology classes, anywhere between 7 to 8 out of every 10 students tend to be female. But just because females are more frequently occurring in a psychology class does not mean they're inherently better at psychology or better in general. It just means that they occur more frequently. And that similarly, if you were to do math and science, there's a greater loading of males relative to females. That wouldn't mean that males are inherently better at math. It just means there are more math majors. Same thing with sports position, who's more important, a quarterback or a running back? That's a silly question. Anyone who follows sports knows that in football, you need both. And if you don't have a running back, then all you can do is throw. and then you're one-dimensional and the team can strategize against you. Or if you only have a running back, you don't have a quarterback, all you can do is run. So once again, you're one-dimensional. So position, there's no position that's better than the other. Political party, whether you identify as Republican, Democrat, Independent, Libertarian, Green Party, doesn't matter. These are just categories. So we assign names to the categories, and that's actually why it's called nominal, in name only, right? But there are no numerical values that are meaningful other than frequency. Once we get to ordinal, now we could talk about greater than, less than, better than, worse than. We could put you in rank order. So when you think ordinal, think rank order. So an example might be if you watch swimming. There is going to be a person who gets a gold medal in the Olympics, a silver medal, and a bronze medal. We know that the person who got the gold medal completed the race in the shortest amount of time. They were the fastest, followed by the silver medalist, followed by the bronze medalist. So we know that there is a better ranking or better score or a quicker race. We can rank order you. But does it necessarily have to be that the distance between the gold medalist and the silver medalist is equal to the silver medalist and the bronze medalist? The answer is no. And a good example of this, if you watch the 2008 Beijing Olympics, you would see Michael Phelps won 8 gold medals in that race. And there were times when he was 3 body lengths ahead of the next person. And then between the silver and the bronze, it was just a fractional finger's breadth, a touch of a finger. So the distance, the biggest problem with rank order is we can put you from highest to lowest, greater to lesser numerical values, but the units of measure are not equal. Same thing when we talk about hotel ratings. Think about a 1-star hotel and what you get for that 1 star, and compare that to a 2-star. There, even from a 1-star to a 2-star, there's a massive jump in amenities. And then from a 2-star to a 3-star, there's another jump, maybe not as much as from a 1 to a 2. And then from a 3 to a 4, it's a little more subtle. And then from a 4 to a 5-star hotel, it might be very negligible, the difference. So we know 5-star hotels are better than 4, and 4 are better than 3, 3 are better than 2, and 2 are better than 1. But the distance in quality is not equal. So rank order, ordinal data puts you in rank order, but you lack equal units of measure. And I emphasize that because when we have an interval scale, now we have equal units of measure. Now, the distance between one and the next is equivalent. However, when we have interval scale, we do not have an absolute 0. So 0 does not necessarily mean 0. And I'll give you 2 examples. In temperature, 0 degrees Celsius is still 32 degrees Fahrenheit. So 0 is not actually 0. You can have sub-zero temperatures. An absolute 0 point, there would be nothing below it. So when we talk about temperature, it's a good example because even 0 degrees Fahrenheit is not the absence of temperature. You have to go deep into the Kelvin scale to find the absence of temperature. So when you have a 0, it doesn't mean it's an absolute 0. There still is some level of that characteristic. So in the case of Celsius and Fahrenheit, we're talking about the characteristic of heat or temperature or friction, movement of molecules. But a more practical example related to psychology is that in IQ, IQ points are equal, one IQ point distance between 99 and 100 is still the same as one IQ point between 129 and 130. So one IQ point is one IQ point is one IQ point. But a 0 on an IQ is not the absence of intelligence. What that means is that instrument could not assess that level of intelligence. So that's a good example related to psychology. Unless you're not breathing, you have an IQ. Everybody has an IQ. You have some level of intelligence. Now, ratio, if you look at the word ratio, the last letter is O. I ask people to underline it, think O as a mnemonic for an absolute 0. 0 means 0 now. So if you get a 0, that's the absence of that trait or absence of that performance. So if I give you a test and you get a 0 on that test, that means you got nothing correct. So that 0 is an absolute 0. Or weight has an absolute 0. If you look at a scale that's properly calibrated, it starts at 0. And then when you step on it, it gives you your given weight. Now, pounds are equal. A pound is a pound is a pound. And when nothing is on the scale, it should be calibrated to 0, the absence of weight. So that's a good example of ratio as well. Now, understanding your scales of measurement is important because in lecture 13, we're going to talk about how your scales of measurement impact the kind of statistics you can do. So when we talk about nominal measures, you rarely have meaningful quantitative data. The best inferential statistic you can do is chi-square, which is a non-parametric statistic. And we'll talk about that at a later point. Whereas interval and ratio scales, that's the gold standard, because now we can get means and standard deviations and do virtually any statistical test we want with them because we have equal units of measure. And then the one that's sort of like sometimes you can use it, sometimes you can't, is ordinal data. And I'll talk to you more about that at a later point. Now, at this point, I want to talk about examples of a nominal scale versus interval ratio scale. In nominal, you just put people into categories, right? So if you were to ask, rate this picture, is the person attractive or not attractive? Just check. Well, now you put them into a category, right? Whereas interval ratio scale might be rate them on a scale of 0 to 10, 0 being very unattractive, 10 being model-esque or very attractive. A person can give a score and you can get an average score for that. So you could see how the questions are asked are going to impact the kind of statistics you could do, and take note the kind of coding you're going to do in SPSS. That seems to be a good place to stop. So let's stop the share here and let's stop the recording. And till next time, everybody, take care.